Today we are going to discuss about velocity potential function. What is the definition of velocity potential function? It is defined as the scalar function of space and time such that its negative derivative with respect to any direction gives the velocity of flow in that direction. Right? It is denoted by pi. It is denoted by pi. Mathematically, this can be written as, right, once again that velocity potential function, it is defined as the scalar function of space and time. Its negative derivative with respect to any direction, its negative derivative with respect to any direction gives the velocity component in that direction. That means the velocity component, the negative derivative with respect to x direction gives the velocity component in that direction. And one more, the negative derivative of stream function with respect to direction y gives the velocity in that direction. Are you clear? And one more, the negative derivative of the velocity potential function with respect to z direction gives the velocity w. Right here, u, v, w are the component of velocities in the directions x, y, z respectively. Right? The negative derivative with respect to any direction gives the velocity component in that direction. That is the velocity potential function. Right? This is u is equal to minus v is equal to w is equal to, here u, v are the velocity components in x, y, z directions. Velocity components in cylindrical coordinates, these are the velocity components in x direction, in y direction, in z direction. Velocity component in x direction, u is equal to minus of dou phi by dou x. Velocity component in y direction, v is equal to minus dou pi by dou y. Velocity component in z direction, w is equal to minus dou pi by dou z. These are the velocity components in x, y, z directions. Now we are going to determine the velocity components in cylindrical coordinates. Right? Here, this is VR. VR is that is the radial direction. Velocity component in radial direction. UR is equal to dou pi by dou r. This is the velocity component in radial direction, and velocity component in tangential direction, u theta equal to 1 by r dou pi by dou theta. These two formulas are useful where we are going to solve the problems. Right? The velocity components in cylindrical polar coordinates, so ur is equal to dou pi by dou r, u theta is equal to 1 by r into dou pi by dou theta, where ur is the velocity component in radial direction, u theta is the velocity component in tangential direction. Laplace equation. Right, here we know the continuity equation first. Once in the continuity equation, the velocity components u, v, w with respect to directions x, y, z. Right? How to derive the Laplace equation? Right? We know the continuity equation. What is the continuity equation? Already we have derived. Continuity equation is equal to dou u by dou x plus dou v by dou w plus dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is the continuity equation. But based on the velocity potential function, we have one more relation, that is u is equal to minus dou pi by dou x, and v is equal to minus dou pi by dou y, and w is equal to minus dou pi by dou z. So these values are substitute in place of u, v, w. Then dou by dou x of u is nothing but minus dou pi by dou x plus dou by dou y of v is nothing but minus dou pi by dou y plus dou by dou z. W is nothing but minus dou pi by dou z. This is minus dou pi by dou z is equal to 0. Is equal to 0. Right? First we have taken continuity equation. In continuity equation, in place of u, v, w velocity components, we have taken the values of u is equal to in terms of velocity potential, v is equal to in terms of velocity potential, and w is equal to in terms of velocity potential. We have one relation that are substituting here. Finally, we have the dou square pi by dou x square plus dou square pi by dou y square plus dou square pi by dou z square is equal to 0. This is the Laplace equation. Dou square pi by dou x square plus dou square pi by dou y square plus dou square pi by dou z square is equal to 0. This is known as Laplace equation in three-dimensional flow. Right? Right? This is the continuity equation. Substituting values here. Finally, we have the Laplace equation. Dou square pi by dou x square plus dou square pi by dou y square plus dou square pi by dou z square is equal to 0. This is in case of three-dimensional flow. Whereas in case of two-dimensional flow, this term is equal to 0. That means the velocity in the z direction, in case of two-dimensional flow, the velocity component in the z direction is equal to, that means w is equal to 0. Therefore, this term is equal to 0. Then we have the, in case of two-dimensional flow, the Laplace equation is equal to dou square pi by dou x square plus dou square pi by dou y square is equal to 0, because this term is cancelled, because in the z direction there is no velocity component in case of two-dimensional flow. Right, one more point, if any value satisfies the Laplace equation will corresponding to same case of flow. That means if the satisfies this equation in case of two-dimensional flow, if the satisfies this Laplace equation in case of three-dimensional flow, the flow is a possible case of flow. That means the flow is steady, incompressible, irrotational flow. Right? This is about Laplace equation. Now, properties of the velocity potential function. Right, here we are going to take the rotational component in x, rotational component in y, rotational component in z. First we are going to take the rotational components. How to derive, how to write the rotational components, I will give you some hint here. Rotational component in x direction is equal to, right, we know the velocity in x direction u, velocity in y direction v, velocity in z direction w. This is x direction, this is y direction, this is z direction. This is very clear. Now, velocity component in x direction is equal to, x direction means this is a u. U, before u, w, after u, v. That is velocity component in y direction, velocity component in z direction. dw by minus dv divided by the direction given here, dv by dt, that is equal to dy, dw by dt, that is equal to dz, and multiplied with 1 by 2. This is the velocity component in x direction is equal to 1 by 2 into dw by dy minus dv by dz. In the similar way, that is equal to velocity component, rotational component in y direction is equal to, this is the y. What is the before y? U. That means du minus after, that is equal to dw. Now we are going to take this direction, this is the z direction, that is equal to dz du is the x direction, this is equal to dx into 1 by 2. This is the velocity component in y direction. Are you clear? Third point, the velocity direction in z direction, that is equal to wz. Right, here also, already I told you, this is the w before v, after w. That means dv minus before v, after du. Right, now we are going to take, this is the velocity in x direction, corresponding direction we are going to take here. This is the velocity in y direction, here we are going to take dy into 1 by 2. This is the velocity component in z direction, velocity component in x direction, velocity component in y direction, velocity component in z direction. These are the values. Wx is equal to 1 by 2 dou w by y minus dou v by dou z. That is the x direction velocity component. Rotational component in x direction, rotational component in y direction, rotational component in z direction. These are the rotational components. Now we have the rotational components. This is the rotational component x direction, y direction, z direction. And also we know the u is equal to some value with respect to velocity function, and v is equal to value with respect to velocity potential function, and w is equal to minus dou pi by dou z. So in place of u, this is w, this is v, u, w, v, u. So in place we are going to substitute these values. So finally we have the rotational components. Right? Wx, rotational component in x direction, is equal to, x direction is 1 by 2 dou w by dou y minus dou v by dou z. Right? 1 by 2 dou by dou y, w is nothing but minus dou pi by dou z minus minus dou by dou z. V is nothing but minus dou pi by dou y. V is nothing but minus dou pi by dou y. This is equal to 1 by 2 taken out, then minus of dou square pi by dou y dou z plus dou square pi by dou y dou z. This is the rotational component in x direction. Similarly, rotational component in y direction. Right here, rotational component in y direction is equal to 1 by 2. 1 by 2 du by dz minus dw by dx. In place of u, they have taken minus d pi by dx, and in place of w, minus d pi by dz. Right, that are taken here. This is one, this is another one. Finally, the rotational component in y direction is equal to 1 by 2 minus of dou square pi by dou z dou x dou square pi by dou x dou z. Right. Similarly, in case of z direction also, the rotational component equal to 1 by 2 minus of dou square pi by dou x dou y plus dou square pi by dou y dou x. These are the rotational components in x, y and z directions. Right. Now, if velocity potential function is a continuous function, if pi is the continuous function, then wx is equal to, this is the formula already I have derived, 1 by 2 minus dou square pi by dou y dou z plus dou square pi by dou z dou y is equal to 0. If pi is the continuous function, this is equal to 0. Automatically what is happening? That is equal to 1 by 2 dou square pi minus of dou square pi by dou y dou z plus dou square pi by dou z dou y into pi is equal to 0. So this is move this side, this is also 0. Therefore, dou square pi by dou y dou z is equal to dou square pi by dou z dou y. Are you clear? This is equal to, this is minus value, this is plus value, is equal to 0. Is equal to 0. Therefore, dou square pi by dou y dou z is equal to dou square pi by dou z dou y if pi is the continuous function. Similarly, this is in the rotational function in x direction, rotational component in x direction. In case of rotational component in y direction, this is the rotational component y direction, and z direction. This is the rotational component in x direction. This is we have. Similarly, rotational component in y direction. This is we have dou square pi by dou z dou x is equal to dou square pi by dou x dou z. Whereas in case of z direction, dou square pi by dou x dou y is equal to dou square pi by dou y dou z. Therefore, the rotational component wx is equal to wy is equal to wz is equal to 0. This is the equation we have derived. The rotational component in x direction is equal to rotational component in y direction is equal to rotational component in z direction is equal to 0. This equation, this is known as a irrotational function, irrotational flow. If the flow is irrotational, wx is equal to wy is equal to wz is equal to 0. Otherwise, the flow is rotational flow, right? Then properties. This irrotational flow, this is nothing but irrotational flow. Then properties of the potential function. Only two properties we are going to discuss here. First one, if the velocity potential function pi exists, the flow should be irrotational. The velocity potential function phi exists, so the flow should be irrotational. That will once again I am going to explain where we are going to solve the problems related to this topic. And another property, the velocity potential phi satisfies Laplace equation. If the velocity potential phi satisfies the Laplace equation, it represents the possible case of incompressible irrotational flow. Steady and incompressible irrotational flow. The velocity potential phi exists, the flow should be irrotational and satisfies the Laplace equation. It represents the possible flow of steady, incompressible, irrotational flow. Right? This is about. Now we are going to solve one problem related to the velocity potential function. What is the data given in the problem? Right? The velocity potential function pi is given an expression. What is the pi equal to 5x square minus y square. The velocity potential function y is given an expression pi is equal to pi x square minus y square. Calculate the velocity components at points 4 and 5. Calculate the velocity components means what is u, what is v, and what is w. That means velocity component in x direction, what is the velocity component in y direction, what is the velocity component in z direction. Okay, right. So we know one standard formula, that is equal to velocity u equal to minus dou pi by dou x. This is based on the definition, based on the velocity potential function definition. U equal to minus dou pi by dou x and v is equal to minus dou pi by dou y, and w is equal to minus dou pi by dou z. Right? First we are going to determine the what is dou pi by minus of dou by dou x of what is pi value? Pi value is equal to 5x square minus 5y square. Right? We are going to substitute here in place of pi value, that is equal to 5x square minus 5y square. The differentiation with respect to x, we have the 10x. U is equal to minus of dou pi by dou x. In place of pi, we have taken this value, that is equal to 5x square minus y square, 5x square minus 5y square, and minus this is the answer we have. Okay, then v is equal to dou pi by dou y minus dou pi by dou y. What is the pi value? 5x square minus 5y square. This is equal to this equation differentiate with respect to y. We have minus of minus 10 10y. This is u, this is v, but they want to determine the velocity components at a point, so 4 and 5, that means x is equal to 4 and y is equal to 5. Now in place of x we are going to substitute the 4 minus 10 into 4 equal to minus 40 units, whereas v, velocity component in y direction, is equal to 10y. 10 into what is the y value? Y is equal to 5. This is equal to 50 units, right? The velocity component in x direction is equal to minus 40 units, so velocity component in y direction is equal to 50 units, right? This is about one problem related to velocity potential function. Now we are going to discuss about one more problem related to velocity potential function, right? The velocity potential function psi is given by an expression psi equal to xy cube by 3 minus x square plus y cube x cube y by 3 plus y square. This is the given velocity potential function, profile of the velocity potential function. Find the velocity in x and y direction, that means what is u and what is v. And second question, that show that the pi represents a possible case of flow. Pi represents a possible case of flow means this pi value, this velocity potential value satisfies the Laplace equation, then the flow is a possible case of flow. The flow is a possible case of flow means the flow is a steady, incompressible, irrotational flow. If this pi value satisfies the Laplace equation, the flow is steady, incompressible, irrotational flow, right? First we are going to determine the what is u, what is v based on the given data. Right here what they have given, this is the velocity profile, that the velocity potential function pi equal to xy minus xy cube by 3 minus x square plus x cube y by 3 plus y. But we know one standard formula, that is equal to u is equal to minus dou pi by dou x. U is equal to minus dou pi by dou x. This is as per definition. Okay, that already explained to you. Therefore, u is equal to minus dou pi by dou x, that is equal to minus of what is pi value? Pi value is equal to x y cube by 3 xy cube by 3 minus x square plus x cube y by 3 plus y square. This is pi value divided by dx, right? This is equal to minus of differentiate with respect to x. This is equal to y cube divided by 3 minus 2x plus 3x square y by 3 plus 0, right? Then this is equal to minus into, this is the minus value, this is minus value, this is also minus, minus into minus plus y cube divided by 3 minus 2x minus into minus plus 2x minus into plus minus 3 gets cancelled, x cube y plus 0, right? Therefore, velocity in x direction u is equal to, velocity in x direction u is equal to y cube by 3 plus 2x minus x cube y. This is the velocity component in x direction. Okay. Next one, what is the velocity component in y direction? And also we know one standard formula based on the definition. V is equal to minus dou pi by dou y, right? Now minus of dou by dou y of what is the pi value? X y cube by 3 minus x square plus x cube y by 3 plus y square, right? This is the pi value. Differentiate with respect to y. This is equal to 3y square x by 3 minus 0. Differentiate with respect to y, 0. Then this is x cube by 3 plus 2y. Okay. Then 3 cancel. This is equal to minus into minus y square x minus into plus x cube by 3 plus 2y minus into plus, this is not plus, minus, therefore velocity component in y direction small v is equal to minus y square x plus x cube by 3 minus 2y. This is the velocity component in y direction, right? Okay, they have asked one more question, that is pi represents a possible case of flow or not. So for that purpose, first we are going to take the Laplace equation, right? Right, what is the Laplace equation? Laplace equation, that is equal to dou square pi by dou x square plus dou square pi by dou y square is equal to 0. If the given velocity profile given, that is the velocity potential function pi value satisfies this equation, then the flow is possible case of flow, right? First we are going to determine dou pi by dou x, this equation differentiate with respect to x, right? With respect to x, this is minus y cube by 3, then minus differentiate with respect to x square 2x, and plus differentiate with respect to x, this is equal to 3x square y by 3, differentiate with respect to x, that is 0, right? This is dy by dou pi by dou x. Then dou square pi by dou x square, this is the value. What is this value? First we are going to determine. Dou pi square by dou x square is equal to this value, this term, again with respect to differentiate with respect to x, then this is equal to minus 0, minus differentiate with respect to x, this is minus 2, and this is equal to differentiate with respect to x, this is equal to plus 3 gets cancelled with respect to x, 2xy. Okay, this is equal to dou square pi by dou x square is equal to minus 2 plus 2xy. This is the dou square pi by dou x square. Now we are going to determine dou square pi by dou y square. What is the dou square pi by dou y square? First we are going to determine dou pi by dou y. That means this velocity potential function differentiate with respect to y. Differentiate with respect to y, this is equal to minus 3y square x by 3 minus differentiate with respect to y 0 plus differentiate with respect to y x cube by 3 differentiate with respect to y 2y. Right, this is dou pi by dou y is equal, this is the value, then dou pi by dou square pi by dou y square is equal to this entire value. Once again differentiate with respect to y. Right, this differentiate with respect to y, cancel, that is equal to minus of 2y x minus 0, this is 0, plus differentiate with respect to y, this is also 0, plus differentiate with respect to y, this is 2, this is equal to, finally this is equal to minus 2yx plus 2. This is the dou square pi by dou y square. Now we are going to substitute the values of dou square pi by dou x square and dou square pi by dou y square, that is equal to 0. Automatically the flow in the pipeline is the possible case of flow. Right, what is dou square pi by dou x square? Dou square pi by dou x square is equal to, dou square pi by dou x square is equal to minus 2 plus 2xy plus dou square pi by dou y square is equal to this value minus 2yx plus 2 is equal to 0. Now this is equal to minus 2 plus 2xy minus 2xy plus 2. Right, plus 2 minus 2 plus 2 cancel, plus 2xy minus 2xy cancel, this is equal to 0. Therefore the flow is a possible case of flow.